So something that's going to come up in this section is the idea of accuracy. And with that, it can be good to know, when do we have an exact value versus an approximation? So exact values are the ideas that it's something coming from a definition, or it's from counting how many there are. I mean, the name is kind of in the definition in terms of it's exact. It's exactly that value. Whereas an approximation typically comes from a measurement or some form of rounding. So if we look at these examples here and kind of try to determine whether it's exact or an approximation, it really comes down to, is it coming from counting something, or is it a measurement? So if we're told that a piece of paper is 8.5 inches wide, key is that this value here is coming from a measurement. Someone laid a ruler down and saw that it was 8.5 inches wide. So this would be an approximation. The idea being that how we lay down the ruler, and you can even try this out. If you grab a piece of paper and put a ruler down, you can see maybe you don't get 8.5 inches right away. Maybe your angle is a little bit off. Or maybe with just your eyesight, you see, oh, that looks more like 8.4 inches than 8.5 inches. There's this margin of error that comes through just from humans. Humans laying down a ruler or reading it, or just how we interpret it. So while there should be this machine out there that's making this piece of paper exactly 8.5 inches wide, it might be a little bit off. It might be like 8.5000001 inches wide. It's really hard with our eyesight and our measurement tools to see that amount of accuracy. So with that, that's why we call this an approximation. As exact as they try to be with it, it can be a little bit off in terms of measurement. Now, if I said there are 23 students in the class, this is coming from counting. Like the name is on the list, or the people that I see sitting in the classroom. And this is exact. It's going to be exactly 23 students. There isn't going to be any questioning of a decimal place or anything like that with this number. If we said there were 18 sunny days in June, this is also counting. So you'd have your weather and describing how many days were completely sunny, then that would be exact. Now, maybe you could argue, well, like, what counts as a sunny day? When is it sunny versus partly cloudy? Things like that. But let's just go with the weather station or whatever we're getting our data from. They do clearly say when a day is sunny versus partly cloudy. So with that, that's an exact value. And the temperature right now is 63 degrees. That right there is a measurement. So with that, they're using some form of thermometer, and with that, there are different forms of thermometers. So with that, maybe you're getting a measurement of 63 degrees right now, but your friend across the room is getting 62 degrees. You just have different thermometers. If one of you's sitting in sunlight and one's in the shade, this is an approximation. Okay, so with this, when we're dealing with approximations, we want to have a form of rounding. And we've talked about rounding with decimals before, like rounding to the tenths place or hundredths place, and that can be beneficial. But this new form of rounding that we're going to talk about is with significant figures. So we call them sig figs for short, but they represent significant figures. You might also see the wording significant digits. That's the same exact thing. And we have these rules for what is considered significant and which is considered insignificant. But the idea is that these significant digits give us an idea of the accuracy of our number. So, rule number 1, all non-zero digits are significant. So if the number you're seeing is not a 0, it's significant. So like 1564, every single one of these places holds valuable pieces of information and a level of accuracy. Like we have an accuracy to the thousands place, hundreds, tens, and ones. So for all of those spaces, we have measurements. So that's where we would say we have 4 significant figures, or 4 sig figs. With this one where we have a decimal, same idea. This is non-zero, 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 non-zero. So overall counting, we have 1, 2, 3, 4, 5 sig figs. I'm just going to write 5. So for each of these examples, I'm just going to be counting how many significant figures there are. So that's the number that I'm including down here. So this has 4 sig figs. This has 5 sig figs. All right. So our next rule goes, all zeros between non-zero digits are significant. So if it's kind of sandwiched between 2 numbers, that's considered significant. So like if we look at 8,056, what I would say is, well, I know that 8, 5, and 6 are significant, but now we're going to start talking about when are zeros significant, because there are lots of rules to go with that. And the idea is that this 0 right here is between 2 significant digits, so that makes it significant as well. So that right there has 4 sig figs. This next one, same idea. If I grab my non-zero numbers, so there I have 4 sig figs, and then that 0 is between them, so that's considered significant as well. So this would have 5 sig figs. All right, our next rule for zeros, any zeros to the right of a decimal are significant. So if we look at this 8.00, what this tells me is by including those zeros, if this was some form of measurement, like say this was a measurement from a ruler and I can get accuracy to the hundredths place, the idea is that reading to the hundredths place, I am seeing nothing and nothing come through. And that's significant versus just 8. If I was just measuring to the ones place, that has less accuracy to it than this number right here. Because this shows that we thought about those values there and we actually got measurements of 0 there. Whereas with this 8, we don't know if we look to the tenths, hundredths, thousands place. We don't know what's happening out there. Maybe it is zeros, but without including those pieces of information there, we don't know. So this would only have 1 sig fig, but this 8.00, by including that decimal with the zeros at the end there, because those zeros are to the right of the decimal place, they're considered significant. So this would have 3 sig figs, where just 8 would have 1 sig fig. And then this 23.0050, so let's go through our rules. We have these numbers that are non-zero, 2, 3, and 5. So those are significant. We have these zeros in here that are sandwiched between, or they're just between 2 non-zero numbers. So those are significant as well. And then with this new rule, this 0 that's at the end here, because it's to the right of a decimal place, that's significant as well. So this number right here has 6 significant figures. So, when are zeros not significant? Any zeros to the left of a decimal are not significant. So, like 0.75, so I have these 2 digits that are significant there because they're non-zero. But this 0 at the front doesn't add any information. That doesn't add anything to our measurement. And like I mentioned in a previous video, we could really just write that as 0.75 without the 0, and that's the same exact thing. So this right here has 2 significant digits to it because that 0 does not count. Here, what we would have is we have our non-zero numbers, 5, 9, and 8. We have this 0 at the front here, but really that doesn't add anything, so I can just kind of even do that. But these zeros over here tie to our last rule that we talked about. Any zeros to the right of the decimal place are significant. So for that, these 3 zeros are significant measurements and they add accuracy to our number. So the only 0 we exclude is that 0 to the left. So this right here has 6 significant figures. All right, this one right here deals with what we call trailing zeros. So if you see the term trailing zeros, comes from here, which is the idea of having a number and then a bunch of zeros just following after. And these trailing zeros are not significant unless they're marked by an overbar. So we'll talk about the overbar, but essentially any of these zeros following, not significant. So if we have 52,400, so the non-zero numbers are significant, but then those trailing zeros at the end, not significant. So this would have 3 sig figs. Now what the overbar does, it's telling us that this is actually part of our measurement. We did the measurements and every 0 until the overbar was measured and calculated. Because otherwise we don't know if they looked for accuracy at the tens and ones place here. So that's why we exclude it, kind of similar to how we compared 8 and 8.00. Seeing 8.00, we know they did the measurements there. With just 8, we don't know what else they did. Same thing here with 52,400. It's like, did they even look for accuracy there? We don't know, so we just take those 3 significant figures. But what this is saying is that they did look at the ones place, and if they looked at the ones place, they also looked at the tens place. So those zeros are significant. They're important to the measurement. So with this, we have our non-zeros, and then we have our overbar, and then anything in between is also significant. So this right here would have 5 sig figs. With this one, notice the overbar changed to just the tens place. So with that, we don't know what's happening at the ones place. We don't know if that's a calculated measurement, and if it was, then they would show it with the overbar here. So what's happening with this one is we have our non-zeros, and then we have the 0 with the overbar, but then that's just a trailing 0, so that's not considered significant. So our significant figures, we'd have 4 significant figures there. Now I crossed that 0 out. It is still important, like this is still 52,400. It's just in terms of significant figures, for only 4 count. So those are the overall rules. So typically what I do is I look for the non-zero digits first, see if there are any zeros stuck between those values, and then think about your decimal place and where zeros are landing before and after that in terms of counting how many significant figures you have.